Testing, testing, testing. So this lecture will be labeled lecture 26.1. It is an addendum to lecture 26. And I wanted to clarify an issue that came up in that lecture that is associated with the signs um, or the resulting equations. What I'm going to do is go through quickly again and rederive the equations for acceleration by applying Newton's uh, first and second laws to this system that reiterates what was done in lecture 26. But at some point, I don't feel like I explained why the ultimate result that we got in that lecture was correct in terms of the sign. There was some question, I think I had some confusion in the lecture. And one of the reasons is because, and oftentimes when you see this done in books as well, as I've taught previously, generally speaking, uh, classical physics is taught in such a way that accelerations for kinematics are, when you apply Newton's laws, you write the equation so that you are writing the acceleration so that it is positive. I do that in this case. However, when we introduce the pulley here, because of the direction associated with torque, and again, that's explained in the lectures, torque ultimately gives rise to rotation. But when something is rotating, for example, this pulley, well, let's take a look at this pulley here. I've set the axis up for block one such that and it's a little bit messy here, but it's basically a standard XYZ axis, Cartesian coordinate axis. And generally, we start off with Y in the vertical direction and X in the horizontal. But in this case, we have to switch to a three-dimensional picture. So essentially, Z is coming out of the board. However, I've drawn it so that we have kind of a skewed perspective so that we can see the three-dimensional nature. So in other words, as opposed to having looking straight on to the pulley and having Z come directly out, I'm kind of at a uh, kind of a diagonal view, if you will, or a view that is a scan, so that you can see the three-dimensional nature of the picture, so that the Z-axis, I'm drawing it kind of like this, so that we can kind of see more of a three-dimensional aspect of the picture. Well, again, I'm not an artist, right? So it's kind of mixing really a straight on view and a skewed perspective. But the point is that the pulley is like this, and I don't have anything that's circular, but the pulley is turning around in the counterclockwise direction or orientation, excuse me, as the object is moving down. So when something is rotating, there's no particular in the plane. Basically, it's rotating in the X Y plane. And so for that reason, you can't point to any particular direction in the X, Y, along the X direction or the Y direction. That is a definite direction for the direct direction of the rotation. So for that reason, rotational objects are defined with respect to the plane of rotation. And so the Cartesian coordinate that's perpendicular to that plane is then taken to be the direction of the rotation. So because the object is rotating in the XY plane, the direction that is perpendicular to that is the Z direction. Now, once you establish that the Z direction is going to define the direction of the rotation, you still have two options. Is it going to be defined along the positive Z direction or the negative Z direction? Well, that is taken care of or determined by something called the right hand rule. Again, this is a quick review. All of this is in the lectures. Actually, I think I cover uh, specifically presenting the right hand rule in lecture 25. Um, but in this case, we're going to use something called, there's three ways you can apply the right hand rule. And in this way, I'm going to use the curl point method. So one of the ways you can determine the direction of the rotation the coordinate direction that the rotation is associated with, is if you curl your fingers in the orientation of the rotation,
which is clockwise.
curl, point, then your thumb, then make a fist and point your thumb will point in the direction that defines that rotation. So, um, since the object is rotating in the XY plane, I curl my fingers in the direction of rotation,
which is clockwise.
Curl point, my thin thumb is going to point along the direction of the negative z axis. Maybe looking at it from a two-dimensional point of view might be a little bit better for you. But if I were looking straight onto this, then I'm seeing the y-axis straight up and the x-axis horizontal like so. The pulley is here and it is rotating, as I said, in the
clockwise direction.
So the z-axis is coming directly out of me. So the negative z-axis is into the board. So with the curl point method of the right-hand rule, I curl my fingers in the direction of the rotation, make a fist point. I'm pointing back into the board. So basically, the torque is in the negative direction, and it's causing a rotation that is basically along negative z. So now let's apply Newton's second law for the pulley. Now that we've determined that, in order to work out the direction of the torques and the direction of the angular acceleration. So by Newton's second law, the net torque, this again is for rotation applying to the pulley, is equal to the moment of inertia of the pulley times the angular acceleration. Okay, now I've always taught you when you're applying Newton's laws, to evaluate the motion first. One way that we could think about this is just to look at the acceleration. As I said, I just did that. If it's accelerating such that the rotation is counterclockwise, then I get an angular acceleration that is into the board, curl point. It applies to angular acceleration just as much as it applies to torque. So curl point, the angular acceleration is into the board, so it's negative. All right, so I'm going to place a negative sign here because that's well, let's do it like this. Moment of inertia, and the acceleration in this case is negative based on how I set up the coordinate system. Okay. Now, we've got a couple translations or kind of substitutions we need to make here because I want to write the moment of inertia in terms of inertia, which is mass, and I want to write the angular acceleration in terms of the linear acceleration because ultimately I have to eliminate those quantities in order to solve them with the Newton's laws equations for blocks 1 and 2. So remember that linear acceleration is equal to a radius of rotation times an angular acceleration. So therefore, the angular acceleration alpha is equal to linear acceleration, tangential acceleration divided by r naught. And you can look up the moment of inertia. You can either derive it or look it up. I've already handled that in previous lectures. But the moment of inertia for a pulley, and we're assuming that this pulley is a solid disk. So the moment of inertia for a solid disk is 1/2 the mass of that disk, in this case, m sub p, times the square of the radius. Okay, so when I take that and I place that into this equation, and by the way, I forgot to write the negative sign. I put it in the brackets, but I determined it's negative previously. So this is a negative alpha. Go ahead and put that in. So now I'm going to substitute in equations 4 and 3 into 2. So I'll put a little note here. Equations 4 and 5 substituted into 2. So that's going to yield the net torque I'm going to go ahead and drop the vector notation since I'm putting in signs here. Let's see what's done. Is equal to first 1/2 m sub p times r naught squared. But then alpha is, again, it's negative, and alpha is equal to a, tangential acceleration, over r naught. So one of the r naughts cancels, one, and ultimately then what I have is that the net torque
is equal to a negative m sub p times r naught times a. R naught is missing and is corrected later on in the lecture.
Now, again, the negative sign is consistent with the fact that I've set up the coordinate system so that the direction into the board is negative. And so this is just telling me that the net torque on that pulley is causing it to rotate with a negative acceleration into the board. Okay, so now we have to evaluate the torques. We've only, that's just evaluate, as I said, applying Newton's second law, evaluate the motion first. Once the motion is evaluated, then evaluate the torque, or evaluate the left side, which is either going to be the sum of torques, in this case for rotation, or the sum of forces. Well, how many torques do we have? We have two torques, one associated with tension 2 and one associated with tension 1. Again, by the right-hand rule, we can just qualitatively assess. Well, actually, we've kind of already done that. The direction of the net torque is going to be negative, because we can see that the object is moving. Well, it's moving down, which means that the torque associated with T2 has got to be greater than the torque associated with T1. That is, whatever torque is in the same direction as the acceleration must have the largest magnitude. Otherwise, it would rotate in the opposite direction. So, using what I call the run wrap point version of the right-hand rule, we can qualitatively assess the directions of these two respective torques. The run wrap point method is you run your hand in the direction of the first vector. And again, remember, just a quick review here, what we're doing, and again, this is in lecture 25, torque is defined as R cross F, where R is the vector pointing from the axis of rotation to the point where the force is applied. And in this case, R is the radius of the pulley, and the point that the forces that we're talking about are T1 and T2. And so the point where they're applied is at the edge of the pulley. And the angle between them is 90 degrees. So by definition, then, cross product is the magnitude of one vector times the magnitude of the second vector times the sine of the angle between them. But if the angle, in this case, we're talking about R naught and T, let's go with T2 for right now. But the angle between them is 90 degrees. Sine of 90 is 1. So the torque for T2 is just going to be R naught times T2. Now, that's the magnitude. But the direction you get, as I said, from the right-hand rule. Run your fingers in your finger like an arrow, your hand like an arrow in the direction of the first vector, which is R. So R is pointing from, again, it points from the axis of rotation to the point where the force applied is T naught. So run your hand like an arrow, orient your hand so that you can wrap your fingers and make them parallel to T2. So I'm running my hand like an arrow parallel to the radius vector for that torque, which is R, so that's horizontal. Your hand can only bend one way, so you then orient it so that you can wrap your fingers so that it's now parallel to T2, which is pointing straight down. Once you do that, you make a fist and point, and that gives you the direction of the torque. Run, wrap, point. So T2 has a torque that's into the board, negative z direction, consistent with the direction of acceleration that we previously determined. So T2 is negative. What about T1? Well, this is R. It's pointing straight up along the z-axis. So I take my arm, make it parallel to R for that torque. So run your hand like an arrow in the direction of R1. Orient your hand so that you can make your fingers parallel to T1. So run, wrap, then make a fist and point. T1 has a torque out of the board, and that is in the direction of the positive z-axis. So it's positive. Now, the overall torque is negative. Why? Because the magnitude of the torque for T2 is greater than T1. How do I know that? Because it's rotating. T1 is making it, rotate in the direction. If this pulley were stationary and then I, set up the system and then let it go, T1 is trying to make it rotate in the counterclockwise direction. T2 is trying to make it rotate in the clockwise direction. So then
T2 is greater because the pulley is ultimately rotating in the clockwise direction.
But I've defined it as negative because as I've just shown, it's
pointing in the negative z direction.
After using the right-hand rule. So when I evaluate the right side of this equation, I would evaluate it in the following fashion. T2 has got to be greater than T1, but it's negative. So I would say a negative T2 plus T1 equals the acceleration that I've already determined for the right side. So I'm just taking the right side down, which is a minus MP over 2 times A. And the torques, the respective torques, are going to be R naught T2. And I didn't work it out explicitly for T1, but it would be the same thing. There's a 90-degree angle there. So the magnitude of R naught times the magnitude of T1 times the sine of the angle between them, which is 90. Sine of 90 is 1. So T1 also has a magnitude, or T1 has a magnitude of R naught times T1. So when I put those in here, what I'm getting is that a minus R naught times T2 plus R naught times T1 equals a minus M sub P over 2 times A. So this is what I don't necessarily think, but this is what I was pointing to in the lecture. There are two negative signs which kind of cancel out in a way, at least that's the way I see it, and then ultimately gives the equation that we got that I got in that derivation. But I didn't really go through the specifics of that because it's just something that, you've done this so many times, you kind of know how it's going to work out. And I kind of did that very quickly without explicitly showing why it works out that way. I think I alluded to it by saying there are two negative signs, but these are the two negative signs that I was talking about. One associated with just the motion of the object, because that's the direction which is rotating. But also, that's why I give you the first negative sign, which is this guy I showed here. But then the second negative sign comes as a result of evaluating the torque, understanding that you have defined the axis in a particular way and that these individual torques will work out such that you get this negative sign over here for T2. Ultimately, then, when essentially I can clean this up by multiplying through by a negative sign, just multiplying this negative sign through by both sides. And when I do that, I get that T2 times R naught, right? Because when I multiply through by a negative sign, that becomes negative. I'm sorry, this term becomes positive. Then minus T1 R naught, and then plus
plus 1/2 M sub P times R naught times A.
So I'm back to the convention of writing the acceleration term as a positive, But when I do that, then I get the resulting equation on the right side. And you can see that this equation 13 is going to be consistent with the equation for the net torque that I ultimately got in lecture 26. So essentially, what I'm trying to do here is explicitly show you with a more rigorous method and why, without kind of leaving out anything, why this equation has the signs that it does, and why that's consistent with the methodology of writing the acceleration so that it's positive. Now, I'm going to go ahead and quickly do just do again uh, the apply the Newton's second law to blocks 1 and 2 to get those equations of motion and then solve them simultaneously to get the final result, which was the acceleration of the system. So, so this is the pulley. So I like that. These equations are associated with the mass with the rotating pulley. But then mass one, I can apply Newton's laws to that. That'll go pretty quickly. So the net force equals mass one times acceleration. Um, so on this, actually, we've got two directions for mass one. We've got the x direction and the y direction. So this is for the x direction. Let's do the y direction first, actually. So in the y direction, the first law applies because there's no acceleration in the y direction. So that's the net forces in the y direction for block one equals 0. And so it becomes somewhat a trivial application because I've got two forces, N1 up, M1A down. There is no acceleration, so I simply have, I'm going to make this equation 14. So I simply have that the normal force minus mass 1 times acceleration due to gravity equals 0. So that gives the trivial result that the normal force is equal to the mass times the acceleration, basically equal to the weight. For this particular problem, that's not always the case, but for this problem, that's the case. So that's the x direction. Now, in the y direction, I have the second law. Why? Because I know it's accelerating in the x direction. In the x direction, I have the second law because it's accelerating in the x direction. So there I have that the net force for block one in the x direction equals the mass of block one times acceleration. Now I've got two forces, T1 and F. Again, we're writing the acceleration so it's positive. So I'm going to subtract the smaller force from the larger force. I know that T1 is larger than F, the friction. Why? Because it's accelerating in the direction of the acceleration. So T1 is pointing in the direction of acceleration, so it must be greater. So I'll then write that T minus T1 minus F is equal to M1A. Okay, F is by definition is equal to mu divided by mu times the normal force. But from equation 16, I've already determined that the normal force is M1A, so I can substitute that in. So what I have is T1 minus mu M1 M1G. So M1G is equal to M1A. So T1 minus mu M1G, the normal force, equals M1A. And that's as far as I can go with block one. Block two, again, second law applied. Why? Because it's accelerating. In this case, M2G is greater than T2. How do I know that? Well, because it's moving in the direction. It's accelerating. The object to block two is accelerating in the direction of M2G. So it must be greater than T2. Otherwise, the thing would accelerate up in the direction of T2. So what I write is, start is by writing out the law, so 21. Net force for block two is equal to M2 times A. And again, I'm writing M2G minus T2 for the reasons that I just mentioned equals M2A. And so I've got um, I see something, I dropped an R here. Going back to equation 10, when I substituted in the accelerations, these substitutions here, there's still an R1 that I have left here, this R1 here. No, sorry. Um, yeah, I guess it was from here to here. So I canceled out an R naught and an R naught from the numerator and the denominator, but denominator here and the numerator here. But there's one left, so there is still one over here. And there should be one here and here. Sorry, I see that. And so there's still an R naught here. So what I was about to say is that there are three equations now that I have to solve simultaneously because I have three unknowns. I'm equally determined now and the unknowns are T1, T2, and A. And I have that between these three equations. Equation 13, the Newton's second law applied to the pulley. Equation 20, Newton's second law applied to M1. And equation 22, Newton's second law applied to M2. Now, that R naught was important because it cancels out of all of these. If not, it would, well, it's a known value, presumably, because you have R naught there. Usually you're given the mass and the radius of the pulley, so that would be a known value. But, so that wouldn't be a problem in terms of solving. But the issue is that it does cancel out this equation because that was one left over from back here. So, there's a couple ways that we could solve these equations simultaneously. But I think the way that I like to do it is just, well, what I'm going to do first is just write equation 13 down again as 23 with the R naught canceled out. So again, R naught is canceled out of all three terms. So I'm just left with T2 minus T1 equals M sub P divided by 2 times A. So one of the easiest way to solve these three equations simultaneously, and I guess namely now it would be these three equations, 20, 22, and 23. One of the easiest ways I see to do that is it's just as simply equation 20 is well, I could solve equation 20 and 22 for T1 and T2 respectively, and then substitute those into equation 23. I would have then eliminated the unknowns for T1 and T2, and I can just simply solve for A. So that's what I'm going to do. I believe that's the way I did it in lecture 25 anyway. In lecture 26 as well. So we'll just do that here. So from 20, solving for T1, I just get that. I'm going to label this 24. T1 is equal to M1A plus mu M1G. And from 22, T2, solving for T2 here. So T2 is going to be equal to M2G minus M2A. Now I kind of skipped a step. I did a step in my head there. So just have to take this M2 over. It's minus, but then there's a minus sign here that you have to translate through. So you're going to get that. So as I said, now I can take 25 and 24 and stick it into 23. So that's what I'm going to do. When I do that, I get, so basically 24 and 25 into 23. So that'll be equation 26. So I'm going to get, so T2, which is just this guy, so it's going to be M2G minus M2A. Now I'm going to take 21 and or 24 T1 and put it in here, but there's a minus sign there, so I'm going to do it in two steps. I'm going to do that in my head. I'll put brackets here or parentheses. So T1 is going to be this guy, M1A minus, plus mu M1G. I'm going to go ahead. So that's going to be equal to M sub P over 2 times A. Now I need to translate through the minus sign. So it's going to be M2G minus M2, or distribute at least, mathematical term. Distribute the minus sign through. So minus M1A minus mu M1G equals MP2A. My notes make sure I didn't make any minus sign errors here. Yeah, I think we're good. So it's just a matter of cleanup now. I can put these terms together, and the terms of A, I need to separate quantities. Get everything with A on one side and everything that's a term of G on the another side. So these terms will go together. So this will be M2G minus mu M1G equals. Now I have basically these terms, two terms will go on the other side of the equal sign and they will become positive. So everything over there will be a positive. So I have M2A plus M1A plus what I have that's already there, M sub P over 2 times A. Now I can divide out the G, factor out the G from both terms. So that's going to be M2 minus mu M1. And again, factor out A over here. So A times M1 plus M2 plus MP over 2. And so my final, final result for the acceleration of this system is going to be that the acceleration A, just by dividing through. Now, what I want to point out here is that this is the sum of the mass of all the objects. That's actually the inertia of the system. Remember, back during the first week, we defined inertia as resistance to change in motion. So presumably, the acceleration should be less than it was whenever we had the ideal pulley here. Because with the ideal pulley, we assumed that the pulley was massless. If you go back and look at this same problem where we had, say, no, where we had, well, we, a couple different versions. One is no friction and no pulley, but then another was with friction and no pulley. So either one of those you can look at, you're going to see the symmetry difference or the symmetries associated with the final solution, but also the subtle differences. But let's say we're comparing it to where there was friction, but no pulley. Well, in that case, um, the MP is going to be 0. So the total of the inertia of the system, the total inertia of the system is just going to be the sum of the masses of the two objects. In this case, and so because that's less, you would assume that everything's staying the same, the acceleration should be greater. That's going to show up in the solution. Let me show you what I mean. So when I go through and divide by this total inertia term in order to solve for acceleration, my final result would be the following. G times, in the numerator, we're going to have M2 minus mu times M1 divided by this inertia term, M1 plus M2 plus M sub P over 2. Okay, so that's our solution. So let's evaluate that based on the points that I was just making. The numerator, if that numerator increases, then the total number decreases. Why? Because we're dividing by the numerator. So in this case, the total of inertia of the system is the sum of the sum of the masses of the blocks plus half the mass of the pulley. If that mass goes to 0, then the numerator increases and sorry, if that mass goes to 0, then the numerator decreases, and that means the total number increases, which means the acceleration increases, which implies that if I have an ideal pulley, everything being the same, the coefficient of friction is the same, which means that the frictional force is the same. Everything being the same, using an ideal pulley, the acceleration of the system increases, which it should, because by the total inertia decreasing, remember inertia being resistance to change in motion, if the resistance to change in motion decreases, then that means the acceleration should be greater. So the mathematics is telling you that. Again, this is why I press students at this level to break out of the habit of just sticking in numbers like you do in high school and make an effort to get used to manipulating the symbols and working out the algebraic symbols and finding a what I call an analytical solution so that you can evaluate the physics. Again, remember, mathematics is the language of physics, not arithmetic. So if I put numbers in all that, I begin to lose essentially what it represents physically. Now, I know it's sometimes a little bit difficult. It looks like chicken scratch when you're just kind of acclimating to all of these symbols and things. But the more you do it, the more you get used to it, and you begin to be able to see these symmetries and the physics of these solutions uh, jumping out at you once you finish, even as you're going through. You see, I try to be as orderly as possible by keeping, numbering the equations, so that when I go back by when I'm studying or just even going back in a lecture, it's easier for me to tell what I remember what I've done, and it's also easier for me to communicate that to you. Now, it may not seem that way if you're not used to doing physics this way or doing this kind of mathematics, just because you're not used to it. So there's a resistance to doing that. But I'm trying to encourage you that if you become acclimated to it as we move forward in the subsequent courses, Physics 37, 38, whether with me or anyone else, I mean, this is just the way it's done. And so this is a classical course, so I'm teaching you classical methodologies. So I would encourage you to try to acclimate to that if you can. Um, but ultimately, when we get the solution, we can see the physics in the solution, and we can compare that to previous solutions, and that helps us to determine whether or not this is a sensible solution. For example, in the numerator, we see that there's this term that's being subtracted from M2. First of all, whenever we did the simplest problem, go back and look at that, where there was no friction and an ideal pulley. Well, it's what I'm pointing out here. If there is no friction, that means that mu is zero. That means that the coefficient of friction is zero. It's an ideal surface, right? Mu is the coefficient of friction applied to this surface. So when that's zero, then this whole term becomes zero. And this reduces to the solution that we ultimately had initially, where I had an ideal pulley and zero friction. M was zero, mu was zero. For that situation, A is just equal to G times M2 over M1 plus M2. So my point is that when we have the analytical solution, if we apply what we call in physics these limiting cases, in the limit that the coefficient of friction is zero, in the limit that the mass of the pulley goes to zero, then the solution that you get here should reduce to a simpler solution that presumably you have worked out before. And if it doesn't, if you get something else when you put in those limiting solutions, it implies that the initial solution you have is not correct. There's some issue with it. Now, there's no guarantee. You may put in the limiting solutions and, I mean, there could be something else wrong, is what I'm saying, but that's a way of evaluating your solution for sensibility. And it's a thing that's done. Again, remember, when you're on cutting edge physics, you don't have answer manuals to look in to see if the answer is right. The only thing you can do is compare it to previous solutions or reduced solutions or limiting cases, assuming that it should reduce back to something that you should know. And so to get in the habit of doing that at this level as a scientist, as a budding scientist, which all of you are, if you're taking this course, um, is a good thing to start doing now. Again, that's another reason why getting analytical solutions are important as opposed to just putting in numbers. Um, so anyway, that's ultimately what I would say with this solution. I believe it's correct. The minus sign also I'd like to put in. It's something that is retarding the motion. In other words, whenever that surface is frictionless, then the weight of mass one is not affecting the motion of the system in any way. But as soon as you relax that ideal circumstance, there is friction now, which now is having a force that's opposite the direction of the acceleration, but also just the weight of the object itself, which is associated with the mass here, or at least the mass times acceleration due to gravity. Remember, I factored that term G out. So essentially, it's not just mass that's here, it's the coefficient of friction times the weight of the object when you take that that G and place it back through. And distribute it back through. And that actually makes sense because think about it. If I were to take my hand and press down on this box as it's trying to move and accelerate, as M2 is trying to accelerate it over the edge, clearly it would reduce the acceleration. If I were to sit on the box while that's doing it or put some other weight on top of the box, it should reduce the acceleration. Just intuitively, that makes sense. Well, the mathematics is telling you that because that's what this minus sign is. Whatever this term is here, it's being subtracted from basically m2 times g, which is the weight of the object pulling it down. So anything that subtracts from that is going to cause the acceleration to be less. So again, this is how mathematics is a language of physics and of science. These things, these signs, these symbols are telling you intuitive things about what's happening to the system over there. So if you can get into a habit of when you get a solution like this, going back and you know physically doing thought experiments or even setting up an experiment, that's an ideal thing. If you can set it up and then do certain tweaks to that design, to that apparatus, and then see what happens to the motion when you tweak it, it should show up in the mathematics. The mathematics is telling you this is what will happen if you know how to read it. So I hope that helps. I hope that helps explain a little bit more of the details of lecture, uh, of the results that we got in lecture 26, and more specifically, the reason that I wanted to give this addendum is I wanted to be a bit more clear about the signs associated with the application of Newton's second law to the rotation of the pulley so that we can see how it works out with those two minus signs, essentially canceling out and giving the result for that torque equation that we ultimately use to solve simultaneously with uh, the analogous equations for blocks 1 and 2. So I hope that helps. Thanks.